Hello and welcome back to the Oxford Online Maths Club. My name's James Munro and I'm here today to tell you about some mathematics. That's the name of the game. Great to have you with us for another episode of the Maths Club. I'm going to try and do more audience interaction this time, try and get the audience involved a little bit more. If you're watching live, then you can join us in a Slido chat, which is over at slido.com/OOMC. The live Q&A or chat is underneath me here right now, and I'm going to try and run some polls and some interaction and stuff as well. I saw last week somebody said do more interaction, so I'm going to try and do more interaction. It's just me on the stream today. I don't have a guest with me on stream today, but that means that I get to decide what all of the maths is. I'm in charge. There we go. Right. Hello. Quick shout out to people in chat. I've seen Athena and let's scroll. Who have I said hi to? Hi Athena. Hi anonymous person. You can be anonymous in the Slido. Hi Lucinda. Hi Michael. Hi Karen. Hi Michael again. Hi Erdish. There's some people in chat talking about their favourite guests from previous live streams, which I didn't ask, but there we go. Hi Lucy. Hi Leah. Right. Okay. Let's see what's going on today. So coming up. I've got a section on the chain rule, which has come up a few times before on live streams, and I thought it was probably time that we talked about the chain rule. After the chain rule, so it's a little bit of maths. After that, I've got more rules and counting. I've got counting problems as well. I want to talk about stuff from before. Hi, in the meantime, to Kets, anonymous again. Jessica in caps lock and another anonymous person. Brilliant stuff. I've got more rules. I'm going to revisit a problem from last week, but don't worry, if you weren't here last week, then I've got, and I'll put it back on the screen again, like that. Trying to do two things at once. Joining me in chat today are two current students, Flora and Zakai. If you've been to episodes before, you might have met them before. They're going to be here to chat to you about mathematics, chat to you about what's going on at the stream, or if you want to talk to them about being Oxford students, then you can talk to them about that. They are over there. If you ask admissions questions, then those end up going to me. I'm going to do some of them live if I see admissions questions, but mostly when I see admissions questions, I leave them until afterwards. So if your question doesn't get answered live on stream, then I might come back after the end of the stream and come back and answer that. People put calculus less than 3 in the chat, which I think means I think is a good thing. Right, let's launch a poll very quickly. Let's do 2. I've got a couple. Let's do 2. So I'm kind of interested. This is episode 7. I'm kind of interested in whether people have been to previous episodes or not. Oh, people are voting for first time here live. Brilliant. That's what I like to see. There's a bit of lag, by the way, between Slido chat and the live stream. Okay, let's just use this moment to have a quick check of my live stream settings. I've got a warning message in YouTube, but it's not the normal warning message I get. A bitrate is lower than recommended. Maybe that makes me all grainy and low quality, but you're not missing very much. Right, okay. We're voting on have you been here before. It's always nice to see new people. Welcome to Oxford Online Maths Club. Don't worry, there are previous episodes. You don't need to watch them in order. You don't need to watch all of them. If you want to see them, they're on the club website. If you want to see some other bits and pieces of maths, including sometimes with guests. Let's let that run a bit because people are voting in that and the options are jumping around. And oh my goodness, there are 100 people here? Is there a way to vote multiple times, or are there just way more people here than I thought? It's like 100 people. And the current, I love this, just trying to explain my audience to other people in maths. The current audience, the vote winning, the 2 most popular options at the moment are, it's my first time, hi, nice to have you with us, and I've been here almost every week. Sort of not much in between, but I've seen a few, I've seen it once or twice, or in between a little bit. Every episode, people have been here all the way through, 26. Right, okay. Amazing to have everyone with us. As people come back a bit, I start to learn the names a little bit. I'm going to try and change this. I want to keep that going. I'm going to try and change. There's partly no guests, so that I practice fiddling around with this. If I scroll out, can I set this to? Yeah, I can set this back to the chat, and then fix it again. There we go. It's a little bit fiddly, but what are you going to do? What are you going to do? Okay, that was my first one. Trying out whether people are here or not. Wow, first time and every episode is both doing really well there. Cool. Right, okay. And people are saying nice things in chat as well, which is nice. What percentage of an engineer's skill set is maths? I think I'm going to come back to that one because I don't know much about engineers. I'm going to go and talk to the engineers, I guess, and come back. Okay, right. Almost said welcome to Oxford. Yeah, I almost say welcome to Oxford every week. Right, okay. I'm going to run a different one. We're going to talk about the chain rule first. Normally this maths club does super curricular mathematics, so things kind of outside of the curriculum. This is going to be very close to maths that's in the curriculum. In fact, this is going to include some maths that's actually in the A-level curriculum. So I thought about not doing it because it's not quite on brand with super curricular. But I want to try and take it in a little direction as well afterwards, which involves telling me the thing. Okay, I'm going to stop this one here because it's actually drawing between first time live and almost every episode, which is amazing. Right, let's launch a different poll. I don't know, yeah, so I'd like to know what you already know about the chain rule. This is my next section on the chain rule. What do you already know? Do you know what the chain rule is? If so, I guess the options are, I don't know what the chain rule is, I know what the chain rule is, or I know all about the chain rule, including your fun extension bit that you're going to do in 10 minutes time. So those are kind of the options, I suppose. And people are already voting for doing extra options as well. Okay, so we've got a good mix between don't know what the chain rule is, which I want to cover. I want to show you what the chain rule is from A-level maths or equivalent. And then a few people also saying they already know what the chain rule is, which is great. And then a fair few people have immediately voted, and they were the first people to vote as well for I know all about this and higher dimensional versions. Okay, so this first half an hour section is going to be incredibly trivial for people who have seen everything before. Who knows? Right, okay, people are voting incredibly fast, and it's about 50-50 split between people who have seen the chain rule and people who haven't seen the chain rule. So I'm going to try and do a bit for each of you. I worry a little bit that in lockdown or in coronavirus times, that maybe there isn't so much time to tell people why things are true. So I'm going to try and show you why some things are true as well, just a little bit. That's the first section. Then afterwards, as I said, more rules and counting problems. Right, that's a packed schedule. Did this change every time I launch a poll? This changes back to showing the poll instead of showing chat. Well, you don't get to see, you'll have to go down here and click that and then scroll back in again. That's not a great system that I've got there. It's cobbled together from different bits of technology. Right, okay, what's going on in chat? People want Lauren back as well. Ah, okay, cool, right. Good. People showing love for ambassadors is fantastic. Good stuff. Right. When would this be taught in A-level? I think this is taught, back in the day it would have been in C3, so a second year of A-level single mathematics. If you're learning A-level single mathematics over the course of 2 years, so sort of at the start of year 13 in normal times, if you're learning single mathematics over the course of 2 years. If you're learning all of mathematics in 1 year, then maybe you've already seen it. Maybe that explains a 50-50 split. Who knows? Let's have another look at that poll. Okay, people are seeing where I'm going with this. Right, okay. I'm going to put a question on the board. I don't have a poll for this. The question's not obviously about calculus. That's kind of the idea. Right, I've waffled too much. I've spent too much time talking. Here's the problem. Oh no, here's an advert. Further reading. Every episode has a little bit of further reading, just a little bit. It's not homework. It's not really homework. A little bit more if you want to read more about the topics, or if I think of something that I should have said in the live stream but forgot to say. Those are posted on Friday, so that I can add in all the things I forgot to say live. It was posted on the Maths Club website. So if you go to maths.ox.uk/r/club, then you can find that. We post it on Friday, so if you check back on the weekend, you can click read more under an episode to see some more stuff that's related to whatever we did. Okay, right, good. What are we doing? Can we do any trig? I think it's A-level maths, but not further maths. UN. Right, okay. Special with all previous guests. It's going to melt my computer. We'll find out. Right, okay. Problem. I promised a problem that's not obviously calculus. Right, okay, here we go. So the idea behind this problem is that sometimes in the real world, or sometimes in maths problems, related to the real world, I guess, sometimes you have a kind of domino effect in processes where one thing affects something and that affects something else, and maybe that affects another thing. And there's this kind of chain of dominoes that affect each other. And I've tried to build a kind of example with numbers on the slide here. First up, so I'd like to imagine this situation. Whenever x increases by 1, y increases by 2. I thought about putting words on these. Maybe I could put words on these. Whenever the number of dogs in the park, we go. Let's go. Number of dogs in the park increases by 1. The volume. The park gets noisier. The volume of the park. I guess this is in decibels or something. So that's my first rule. Whenever the number of dogs increases by 1, the volume increases by 2. And then secondly, whenever, I guess maybe this could be like the temperature or something. T for temperature, I suppose. If it's a nice sunny day, then you get more dogs in the park. And we've got these 2 quite simple rules that whenever one increases, whenever one of these inputs increases, the kind of output increases. And they kind of change together, right? X changes Y and T changes X. The question is very simple, and some people in the chat are way ahead of me. Suppose T, the temperature, increases by just 1. The question is, what happens to Y? And Lucinda, Anonymous, Billy, Anonymous, and Will in chat have all said it increases by 6, which I agree with. That's what I was hoping what people would say in chat. And somebody's posted a multivariate example already, linking to ams.org. So there you go. There's some further reading in chat for you already. Thank you, Epimorphism. Assuming that is a real link to the MS and not some sort of rickroll. Right. Yeah. So and somebody else in chat has put some calculus kind of looking things where they've put some derivatives decreases by -6. Ketz has put a reason here. 2 times 3 is 6. I like that. They've taken these numbers and multiplied them together. And I think this sort of makes intuitive sense, right? That as you increase one thing, it can cause this effect in another thing. And the right thing to do is to kind of multiply together the rates of change. Cool. Okay. We might look at some other rules at the end, trying to address things that people say in chat, even though the 20-second lag makes it tricky. More people are saying 6, you and Lenora, and Anonymous. Somebody said decreases by -6, which, okay, you got me. Right, okay, I feel like this sort of problem makes sense, right? That it changes a thing, and then every time that changes, it changes another thing. The reason this problem is kind of straightforward or easy, I suppose, is that everything in here is kind of linear. That there's a very simple rule about what happens when you change things. Of course, things in the real world are more complicated than just having a kind of linear relationship that whenever you add another dog, it gets louder by 2 decibels. Actually, I think the relationship might be more complicated than that, depending on, there might be some diminishing returns once the park gets really noisy or something. This might be some more complicated relationship. But that idea holds true as well for functions that are more complicated. The thing I want to do is think first about the change that the input variable has on x, and then think about the change that x has on y, following it through like that. Yes, cool, right. Chat is also talking to each other, which I also like. It makes it feel more like a maths club when people are chatting to each other about different stuff. Right, they're talking about me, which is weird, but never mind. Okay, so for functions that vary and aren't just simple relationships like this, we need a little bit more technology. We need the concept of a derivative. Somebody put some derivatives in chat already, but I'm going to show you some derivatives too. Okay, so here's the setup that you meet in A-level or equivalent. Suppose we've got y equals f of x, which you're familiar with. So you might be familiar with writing things like dy by dx for the derivative, or f prime x, like this, to find a derivative. This is supposed to mean, if you've seen no derivatives before, let me explain what these are supposed to mean. These are supposed to be the rate of change. So this is going to be the chain rule, but this is going to be the rate of change of y, and then it's sort of with respect to x, which I feel like normally when you learn derivatives, this bit sort of gets mumbled under your breath, like this is the rate of change of y with respect to x, but it's important here. So here this is how much y changes as you change x. So as an example, if you have something like a cubic, you learn in A-level this rule about what the gradient is. The gradient is kind of the rate of change, right? So here the cubic's going up, it's going up like this much. If I draw on a kind of tangent, I can stretch out a line at the tangent to sort of see what the rate of change is right over here. So there could be something it's going up over here, and then it's going down in between, and then it's going up again. You learn some rule at A level for a formula for what that gradient is, which is fantastic, really, when you stop and think about it. If I throw a cubic at you, A level students, if I throw a cubic at you like this, then you know how to find the gradient of a point on that cubic without doing without doing geometry, conic section, cubic nonsense or anything. You just know a simple rule for working out what the gradient is. In fact, it's sort of so simple that you don't even have to think about it too much, I think. I don't know. I never know how many people we've got who are not in A-level yet, and whether I should be teaching them A-level maths. But hey, look, the rule is just that you bring the number down the front and you subtract 1. Here, this is x to the 1, so I bring the number down the front. That's 1 out the front. 1 times 1 is 1. Welcome to the maths live stream. X to the 0 is a constant. So the rule for the derivative is this is 3x squared minus 1. Okay, cool. Mumbling, right. Okay, but this problem is more complicated because in this problem I'd like to imagine that x is also secretly a function of t. X equals g of t, we'll say, for that function over there. Okay, brilliant. Hi, look, Maya knows about derivatives. 3x squared minus 1. People are asking emissions questions as well, which I will get back to because I want to give you a proper answer, and it's hard to interlace that into derivatives and stuff. Right, okay. Suppose we have y equals f of x and x is secretly a function of t. I guess the question is, what happens when we change t? And changing t causes x to change a little bit, and then changing x causes y to change a little bit. So that's kind of interesting. That's the same as that problem with the dogs in the park or whatever it was on the previous slide, where one thing changes and that affects the next thing along. Okay, so I guess we could think about how the rate of change, what we saw before, where it was kind of obvious, everyone said 6, right? The rate of change, the thing you do is you multiply the rates of change together. So you take the amount that x changes as you change t by a little bit, maybe by 1 or something tiny. You take the amount x changes as you change t. That's called the derivative of x with respect to t. So we want, I guess, here we go, we want dx by dt for the amount that x changes as we change t, and we want dy by dx for the amount y changes as x changes. And then our plan is to multiply those things together. And multiplying them together should give me dy by dt, the rate of change of y with respect to t. I think I've got that on a slide. Let me see if I've got that on a slide. Yeah, okay. Here's the rule. I've written it out with primes, but I could have written it out like a dx by dt. Do I mean that? No, here I mean dy by dx, excuse me. This one is dy by dx, and this one is dx by dt. So I've sort of written it out one way using the f and g's for what those functions are, if you like functions with primes for your derivatives. If you prefer to write your derivatives stacked up like this, dy by dx, dx by dt, then you might write things like this. Okay, dy by dt is dy by dx times dx by dt. Okay, fantastic stuff. So this is multiplying those rates together for the same reason as we had on the previous slide, that you want to think about how I guess the derivative really tells you, if you're really near to this point, then the derivative tells you if I change the input, then the output changes in a nice linear way to a kind of good approximation nearby. That cubic is really complicated, but very near that point, the rate of change behaves in a nice linear way. Okay. By the way people remember this is that dy by dx times dx by dt, it looks a bit like the dx's are cancelling out, so that it would just be dy by dt. That's not quite how this works. It's more a sign that this is good notation for you writing derivatives like this. And in fact, there are cases a bit like this where just cancelling out the dx's doesn't work, which is why I'm being more careful than just saying, they're fractions, divide the fractions. They're not fractions, they're derivatives. Right, okay, good stuff. So we've got a chain rule that says this thing that kind of on the previous slide everyone was happy with, it just changes by 6, right? You change one thing, it does a little bit of rate of change, and that rate of change gets maybe amplified by the next effect in the chain. You could imagine having more of these strung together, right? Like you could imagine having a really complicated domino effect. I haven't got a slide for this, but you could imagine having loads of them together so that each thing affected the next one in the line. And then the chain rule would be, if you want to find the rate of change of the last thing with respect to the very first variable, then you just go through multiplying together all of the rates of change. I said the word amplified in there because I think I'm imagining a little bit that you can imagine these as different processes, like different processing boxes that apply different effects, and they might pick up a small change and make it larger if one of these numbers is really big. I think this is sort of related to ideas of sort of feedback loops and things. Goodness knows. Right, okay. I think that's what I wanted to say about the chain rule. That bit is in A level. You will at some point learn that from a proper teacher who's actually trained to teach you A level maths or equivalent. This is not a substitute for A level maths. Okay, so you will learn that bit properly at some point. I'm now going to show you other stuff. I've got a couple of examples of the chain rule. When I've told you a rule like this, it's probably a good idea to give you some examples, right? There are 200 people here. That seems a bit unlikely. Let me check my dashboard. Oh yeah, goodness, right, okay. Hi, 200 people. Thanks for showing up. Yeah, so chaos theory does have a link. Someone said chaos theory. We're going to talk about chaos theory on the live stream at some point, I promise. We're going to talk about chaos theory. There's a thing hiding in chaos theory somewhere that's a little bit like this, which is what I'm thinking of. Okay, right, cool. We're doing a bit of understanding. I sort of worry that there's like an obvious way that it works that isn't true. That it's not just the case that you cancel your dx's. I've said that already. Never mind. Right, okay. I've got some examples of doing stuff with this. Oh no, I've got that written up again, but different. Sometimes you see this written like this. If y is f of g of x, stacked together like this. So sometimes people don't bring in the t, they just talk about x as the input variable and you write it as f of g of x. So this means apply g to x first. That's the inside bit. You work kind of inside outwards. G to x, and then apply f to that. And people will write things like, if y is this, then divided by dx is f prime of g of x times g prime of x. Where I don't really... This sort of hides a little bit how it works, I think, but it's much more convenient than writing down loads of x's and d's. And quite often problems that you see are kind of written a bit more like this, where you've got y as some crazy complicated function of x. And you can imagine it, if you like, as being a function that takes that, puts it down in some intermediate variable, and then goes somewhere else. Right, okay, dy by dx does this. It's the same thing, right? With different letters, so confusing. Maybe I shouldn't have both of these. Okay, ooh, someone wants a collab. I think that's the first request for a collab, maybe. Oh, it's got like 4 thumbs up as well. Right, okay, I don't know who free science lessons are. I'm really sorry if free science lessons are watching, but I don't know who you are. I will do some research. Cool, right. Okay, examples. Now I've got some examples. Tangents to an ellipse. Have I spelled ellipse right? Yeah, I've spelled ellipse right. Okay. So you know how to find tangents to circles. You have rules about tangents to circles. I feel like GCSE and A-level don't really tell you much about finding tangents to ellipses. It turns out the chain rule just sort of solves this problem. So I've got my ellipse, and I've got an equation for it. X squared plus y squared over 4 equals 1. It's kind of a stretched circle. So I could rearrange that to be y equals, for this top bit of ellipse, y equals square root of 4 minus 4x squared, which looks a little bit like a function of x. Let's do that one live. Investigation topics for EPQ, or just things to read about that are interesting. I'm sort of hoping that the live stream, and especially the further reading, I'm sprinkling in loads of stuff into the further reading in the hope that someone out there finds it interesting enough to go and read a little bit more about it. If you're looking for an EPQ topic, then kind of the best I can do is throw random bits of maths at you and hope that you see something interesting. It's kind of the whole vibe we're going for with the live stream. We're not going to do implicit differentiation. Somebody already wants to do implicit differentiation. That's something DFAC mentioned before. I'm going to do it like this instead, using the chain rule for my chain rule session. Okay, you're very keen. Right, okay, y equals, I'm going to write it like this, 4 minus 4x squared to the half. This kind of looks like f of g of x, right? F of g of x. I should say, I suppose, I'm finding the derivative here, because the derivative of the curve is the gradient of the tangent line. Should maybe have said that at the top. Okay, it looks like f of g of x, where f is... So there's a potential for this to get very confusing, because... No, I've just written the whole thing out. That was not what I meant at all. I talk and do maths at the same time. F of x is x to the half, and g of x, the kind of inside function, as 4 minus 4x squared. And now A-level kids will know a way to differentiate each of these separately, and the rule that I want to do is just to work out. So on f prime of x, which is 1/2 x to the minus 1/2. Again, people not in A-level maths yet, this bit's just a magic fact you learn at A-level. The rule is you bring the power down, multiply out front, and you subtract 1 from the power. I've done that with the number 1/2. G prime of x is with the same rules. It's this. Now the chain rule is not quite multiply those together. There's a strange bit of notation here that could be a little bit confusing. That I've worked out both of these as if they're functions of x. Actually, what I want is f prime, the derivative, but I don't want it evaluated at the variable x. I'm not passing x to my function f. I'm passing g of x to my function f. So I want this derivative evaluated at, and this is a little bit tricky, I'm going to take this derivative evaluated at the point with g of x. That's the first thing in the chain rule. Okay, so this is slightly awkward. I need to write out this bit. 4 minus 4x squared to the minus 1/2. Okay, and the chain rule says that if I want dy x, I need to take these last two things and multiply them together. So I get 1/2, 4 minus 4x squared to the minus 1/2, minus 8x. Amazing stuff. Can I simplify y to... Ooh, hello. Okay, so I've got all these things multiplied together. That's my gradient. That's the gradient of this tangent. I can now send it through that point. So I've got the gradient of the line, send it through that point, and then find out what the equation of the line is if I want to. I guess I could plug in a value of x if I was particularly interested in, like x is minus 1/2 or something. If I was interested in that, I could plug it into this formula. But I think it's interesting that I've got a formula out, right? I've got a formula in terms of x. Okay, could I simplify this? So people want to simplify this to 2 minus 2x, which is unfortunately not true. Square roots are really weird when acting on kind of polynomial like that. It's not just the square root of each term. There's the year 11 poll. It's not an official poll, but you can give it a thumbs up if you're in year 11. I assume the person asking is in year 11, so remember to add 1 because you can't thumbs up your own comment. Right, okay, we found the equation of the tangent to an ellipse, more or less. There's actually a geometry way to do this. I sort of toyed with not admitting that there's a geometry way to do this, but you know, geometry, it's kind of interesting, right? So this ellipse goes through the points 1, 0 and 0, 2. So it is a stretched circle. Let's clear this and show you. Can I show the eraser? Yes, there we go. It's a stretched circle. I'm going to very quickly show you an alternative way of doing this that doesn't use the chain rule or any derivatives, just because the alternative way of doing it exists and I figure somebody wants to see it. Stretched circle. So what I could do is I could step 1, squash, step 2, tangent to circle, which is easy, we know loads of maths about tangents to circles, and then step 3, stretch. So technically this is going to work because tangents stay tangent when you do stretches and squashes. So one thing I could do is take this problem, with my point x, y over here, I could squash it down to think about a circle. I can find the derivative at this point. Well, the derivative over there is just y over x. Y value over x value. That's the derivative of that's the gradient of the radius. And then I know that that's at right angles to the gradient of the tangent. So the gradient of the tangent, sorry, my handwriting gets worse the more excited I get, will be x over 2 over y, don't forget the minus sign because these things are at right angles, and then step 3, stretch it back again. So I need to take that and double it, halve it, do something to it, stretch it back again, something like that. Might have got, oh yeah, this is, stretch it. I'm just going to say stretch. Do some squash. Do I mean x, y over 2? I do mean x, y over 2. That's why I've got stuck over here. Oh, where were you 20 seconds ago? No, it's the 20-second lag. Oh, that's annoying. Right, you get the idea. You get the idea. I've messed up all my factors of 2. Oh, that's so annoying. Student ambassadors in the Teams chat are going to tell me in 20 seconds as well, right? Oh, my Teams chat has crashed. Right, okay. There we go. X over y over 2. I've made such a mess now. Stretch it back again and you get 4x minus 4x over y, which is an alternative expression for the gradient to the ellipse. Maybe it's good that I didn't try to do it this way first. Right, too excited. Homework, or further reading, try and reproduce what's supposed to be on this slide. Right, wow, what a mess. Great, okay, I think it's almost time for an ad break. Let's do one more example. I want to show you a case where the chain rule is not a good idea. So here I've got powers of polynomials, and it's very easy to come into problems like this and say, aha, I'm going to use the chain rule. I've got x squared plus 1 squared, that's like a function of a function, is like 2x squared plus 1, so bring down the 2, leave this thing alone to get like 2x, but it's not x, it's x squared plus 1, and then this is going to be multiplied by 2 times x, so there's going to be 4x, x squared plus 1. You could do this with the chain rule, like that, and then you could do it like that, but actually for this problem, it's probably easier just to multiply out the x squared plus 1 to get something like this. Sakai Flora, don't worry, my team's crashed. I wasn't expecting you to keep up with the math that was going on, as you're doing a great job in chat. Okay, we're doing good. Probably easier to multiply out, he says, doing the multiplication out. I definitely need an ad break to roll. Right, okay. Probably easier to multiply out and differentiate it term by term, which gives you the same answer. I mean, of course it does. If you get the multiplication out correct. But there are other examples where you don't want to multiply out. So this one's much harder to multiply out, but using the chain rule, it's not so bad. So like a lot of skills that you learn, it's important to have some sense of when you're going to use this skill and when there's a different method. So maybe you're really great at geometry, stretchy, squashy stuff, and you don't want to think about tangents to ellipses using the chain rule at all. Maybe you're really great at multiplying out things to the power of 10 in your head, and you don't want to do it like that either. But the chain rule is going to be one more tool that you've got there. Right, irresponsible chain rule use. I could have stretched in the x direction too. Yeah, so there's a version not on the board where you think about kind of a general ellipse. Maybe that's going to be in the further reading, who knows. Stretching a general ellipse in the A and B directions. Sometimes the further reading just covers stuff that I messed up on the stream and want another go at. So we'll have a go at that. Cool, right. Yeah, and people are correcting my multiplication out now. Am I going to watch a section of a 20-second segment of free time? I'm going to watch it afterwards. Also, oh wait, right, okay, cool. Chain rule, there you go. I've got a higher dimensional version that I'm going to show you after an ad break. So I'm going to try and jump through some slides and show you the ad break so I can take a quick break and catch up with chat a little bit. Right, okay, roll the ad break. Oh, yeah, look at this. So today we're sponsored by Parsifal's Identity. Parsifal's Identity is maths that you learn at university, and it lets you prove incredible facts like this. Let me know in chat if you've seen any other incredible facts like this. Right, just going to catch up with chat a little bit. What does chat want? Isn't that the power rule? Oh, is the power rule got a name? Maybe, ooh. Just use the product rule. Somebody's getting excited by one of my rules in the second half. Use your chain rule with caution when the fun stops. Stop. Great stuff. Okay, I'm gonna watch 20 seconds of free. Ooh, hello. That was loud. 20 seconds of free science because somebody asked very nicely. We're catching desktop audio. We're not good. I can't believe you've done this. I can't believe you've done this. Amazing stuff. Brilliant. 10 out of 10. Right, there we go. Bam. No, actually, let's reinstate that. That was amazing. Right, okay, good. 20 seconds too late. An ambassador has told me I'm getting rickrolled. I thought, why did we approve a rickroll? we have moderation. Best live stream ever. Right, okay. 3 Blue 1 Brown did a video about this. Do not link me to it. Right, great. Have they changed? That's made my day. Right, okay. This is going way over my head to somebody. Good times. Yeah, well, everything we've seen so far, I think you will get a chance to learn properly through A-level maths. I want to show you some other things. I've just put this on the board because I think it's cool. I'm not going to explain it at all. I'm not going to explain where it comes from. I might put a note in the further reading about how the maths works at university, but it uses some serious university maths, so I can't really do it now. Look at me, I can't even multiply out x squared plus 1 properly right now. I'm going to try and show you a higher derivative chain rule, just because I can, and I want to show you something that's not in A-level maths. Okay. Yeah, is it like using primes, Matt Parker? Yeah, so I think people have seen there's a version like this with squares. A version like this with squares that gives pi squared over 6, which is a little bit more famous. But university, we learn a kind of general theory. It's not even a theory about adding stuff together or a theory about pi to the large numbers or something. It's just a theory about functions and their transforms. We learned a nice big theory, and then lots of special cases of it are interesting. So this is a special case of some big exciting thing. Right, okay. I'm going to put something in further reading about this. I'm going to see how much of this I can explain to the live stream. Oh, amazing. Rick Astley has shown up in chat as well, just to rub it in. Right, okay. Chain rule. I love this. Right, okay. I want to do some higher dimensional stuff here. So I want to go back to that original problem we had and make it slightly more complicated. I hope that's okay. So here's another problem for you to think about. Similar setup, different numbers, more things going on. I'll read it out. So here, whenever x increases by 1, y increases by 2. It's just a rule. We're back to things behaving nice and simply. Separately, whenever q, a different variable, increases by 1, y will notice that as well, and it will react by increasing by 4. Those things happen independently and separately. Whenever x increases, y is affected, and whenever q increases, that increases y as well. So I've got two more rules. Whenever t increases, that affects x and it affects q. I'd like to know what the kind of combined effect of all of that is if I increase t by 1. Which course teaches that theory? Goodness, I think that'll be in Fourier series and partial differential equations, which is in first year mathematics, although that might not be the case. It might be in one of the later courses. It might be in a second year course, actually. Good, right. What is the average age of a full professor at Oxford? That's a complicated question that's going to involve me looking up a lot of people's ages. I have no idea. Okay, so we're getting suggestions in. I think I'd like to think about what happens. Yeah, I think I'd like a reason for this one as well. Somebody put a reason earlier that 2 times 3 is 6. People are disagreeing as well. Okay, this one's harder. I like it when people disagree. It's possible that there's more than one way to interpret this. It's possible that my explanation isn't quite watertight. We've got 16, 20, 22, 22 again, 22 retracted. Okay, we got things changing by different amounts. And people giving thumbs ups. Good times. What was the method theory called? It'll be in the further reading, Jacob. So yeah, it was called Parsifal's Identity, which I will spell in the further reading. Increased by 8 or 22. Yeah, so kind of two effects going on here, right? Let's answer some questions while people are chatting. Oh, there we go. People are speeding up a little bit. Analysis at university looks at functions in a general sense and thinks about what a derivative actually is and thinks about the kind of fundamentals of how calculus works. When is it the case that you can integrate a function? Can you always integrate stuff? Do things sometimes go wrong? Can you always differentiate things? Does that ever go wrong? If your function is a random cloud of dust of points, is that different from anything else? Can you do any maths with that? Interesting stuff going on. Okay. People are multiplying stuff together. People are very keen to multiply things together. And some people are, I think there's two camps going on. People are getting about 16 by multiplying stuff together. Yeah, I like it. So someone said dy by dq is 4 and dq by dt. So people are thinking about the chain rule from before, right? Yeah, I like what Beth and Molly are saying as well. Look, it's sort of simultaneous. Great stuff, Beth and Molly. Maybe they know each other, maybe they're in the same classroom, or maybe they're two people who have never met each other typing very similar mathematics at roughly the same time on different sides of the world. Who knows? We're live, anything could happen. Good, and anonymous as well. And Billy. Right, okay. Good. Right, okay. I like the argument they're presenting. I'm going to try and do it in words as well. So when t increases by 1, two things happen. Both of these things happen. X increases by 3 and q increases by 4. Now, when x increases by 3, that's like the top line happening 3 times. So I could multiply this up. Say, if x increases by 3, then y would increase by 6. And if q increases by 4, then y would increase by 16, I guess. I'm multiplying through this second line by 4. And kind of both of these things are happening at the same time. Both of them are happening at the same time. I think both of those effects apply to y. You could imagine one happening one before the other, or at the same time, or sort of taking it in turn somehow, or both of those effects causing y to increase. I think I agree with the people who are saying that 6 plus 16 is 22. I think I agree that these are both separate effects now, but they're both going to change y. So it's something like, let's write that out very carefully, 3 times 2 plus 4 times 4. And it's slightly awkward with statements like this to chase through when are you supposed to multiply and when are you supposed to add. And it's something to do with the following through information through this network of conditions I've given you to work out what the final change is. We've seen 2 of these now. It sort of feels to me like I could come up with really complicated versions of this where you maybe have to think quite carefully about whether you're multiplying things together or adding them together. Okay. Right, good. So I'd like to try and show you a continuous version of this, or a thing with complicated functions. It's going to involve some notation that people haven't seen before, but never mind, just hang on. Here's the setup. Suppose we've got z as a function of x and y. So this has sort of got 2 inputs, which is different. And I've been forced to use more letters of the alphabet. I would have liked to write y is f of stuff, but to keep the letters in kind of alphabetical order. No, I haven't done that at all. Anyway, I've put x and y as the inputs and z as the output. Okay, I've got z as f of x and y. X and y are both secretly functions of time. Well, I need this idea that I want to say how much f changes. How does f change when x changes? And I kind of want that independent of y. And I kind of want that, I kind of want to think about the 2 different things that are causing it to change. How much f changes when x changes, and how much x changes when y changes. There's some notation for that. It looks like this, like a curly d, to mean how much f changes when x changes, independent of y. And over here we could think about how much f changes when y changes, kind of independent of x, thinking about them as 2 independent effects. And then the rule is just what people said it should be, thinking like we did on the previous slide. The rule is that the overall change of z when you change t is you think about the two effects separately. The effect that you get from changing x. So here is how much does x change. X changes with time. And over here, this kind of crazy object that I haven't really explained is supposed to be measuring how much does f change. So f changes with x independent of y. And then there's a separate term for same but y. Then you sort of take these two different effects and add them together. Now I've been very vague on what that object is with the curly d in. It's called a partial derivative because you're, I suppose, only looking at part of the inputs, if that makes sense. I suppose they make up parts of this total derivative when you're working out the z over t or something like that. So these are kind of the parts of the derivative. If you're working out for polynomial, there's some rule that's very similar to the rule you learn at A-level, so you can actually do this. In general, you've got to think carefully about keeping things fixed while you change other variables, and it can get quite complicated. There's loads of brilliant theory to do with these sort of partial derivatives. You don't see any of it at A-level. We've saved it all for university mathematics. It's all fantastic, thinking about how things change, so that you can talk about, I don't know, how the weather changes in different places and how the weather changes at different times. Those are both different effects. They're kind of thinking about changing different input variables to have an effect on the outputs. Okay, what is that symbol? It's a curly D shape. Right, good. Okay, how are we doing? We've got a statement of the chain rule in higher dimensions, and it's 5:15, so I've got a quarter of an hour to do some other stuff. I didn't want to just do calculus. I've overrun a little bit more. People want the product rule. We're going to put the product rule on the board. First, I want to change topic just in case people are finding this incredibly dull and want to see something completely different. I want to talk about this problem from last week because a couple of you wrote in with quite nice solutions to the problem from last week. If you weren't here last week, the videos on the web, the video quality's pretty terrible for last week's video. We had some streaming problems. But the problem is about adding together consecutive positive integers. We forgot to write positive on the slide. There we go, positive. So adding together consecutive positive numbers. And Ariane is trying to do this to make particular numbers. The questions were, and I'm not going to spoil them, which numbers can she make by adding together just 2, just 3, or adding together just 4? Which numbers can't be made? And some people wrote to me, I guess I am going to spoil the last part, sorry. People wrote to me with a little proof that you can't do powers of 2. Shout outs to Sophia and Kevin, who sent me maths to say you can't do powers of 2. So I'm not going to show you their proof right now, in case you're one of the 50% or so people who weren't here last week. Powers of 2 are not possible. It turns out there's a nice proof to say that you can't do powers of 2 by adding together consecutive positive integers. You can't make 8. You can't make 16. I haven't seen a proof yet, and this is a little bit cheeky. I haven't seen a proof yet that all the other numbers are possible. So there's kind of 2 steps to this, right? First, to show that Ariana can't do those numbers, and then also to say actually Ariana can do all the other numbers. Those are technically separate things in a proof. So I'm still looking for a proof for this kind of separate part as well. Oh, there's Sophia in chat. Hi, Sophia. I'm kind of telling people about your proof, but trying not to say your proof. Weird, right? I've got a kind of follow-up that I've come up with. In general, when you're trying to make a number, there might be more than one way of doing it. How many ways are there? Maybe once you've proved that all other numbers are possible. Okay, sure. You can't get 0. That's true. You can't get negative numbers. You can't get complex numbers. Yes. No, true. You can't get other things. Cool. Yes. Other things that you can't do. Yes. Okay. I should be more careful here. I probably want to put in positive in here somewhere. Oh, twice in one presentation missing the word positive. That's not a good look, is it? 1 is a power of 2, and you can't make it by adding together consecutive numbers. So I think that's okay. I think 1 is not possible. 1, 2, 4, 8, 16 are not possible. That's it. Okay. Can you get an even thing? Yes, that's what I thought to start off with. When I set this problem, I thought maybe it's only odd numbers, because when you add together two numbers, you get an odd number. Ariana's allowed to add together 3 or 4 numbers, and if you add together more numbers, you can get other things. Like if you add together 5, 6, 7, 8, that makes 26. So you can make other things like that. So it's not just odd or even, because 26 kind of breaks that. You can form 1. How are people making 1 with the sum of consecutive positive numbers? People are using 0. How do I feel about this? I'm gonna say bigger than 0 in here. I'm gonna spoil everybody's fun. There we go. And more than 1 number, right? Okay, good. Is the proof just that you have to get together 2 consecutive numbers? The result will always be odd. That's part of the proof. But Ariana is allowed to add together 4 or more numbers, or 2 or 3 or 4 or more numbers. In which case, she can make even numbers as well. It's kind of not obvious, right? She can make 36. Why can't she make 32 using some other series of numbers? I can never get a multiple of 4. I think you can get a multiple of 4. I've got one on the board. I've got 36 on the board. Okay, good stuff. Right, okay, I like this. We're sort of solving things live. 0 is not positive and not an integer, some people say. Okay, right, we're going to fight about... I don't want to argue about 0. it's banned now. I've banned it. Yeah, people don't think 0 is positive. Fine, okay. Right, okay. I think I'm going to leave this one in further reading as like an exercise for trying out more stuff, because it's slightly more complicated than I thought it would be, which is nice. Cool, right, okay. Good, we've still got 10 minutes, which gives me time to talk about some more calculus. Can you tell I'm an applied mathematician? I've sort of planned my time, so like, counting number stuff in the middle, yeah, sure, we'll do a little bit, and then calculus maths as well. 0 is definitely a real number. I think real numbers, anything that has a decimal expansion. That's a terrible definition, James. Defining real numbers is something we do in the maths degree as well. Surprisingly difficult. Okay. I wrote it as X. King Richard IV. I wrote it as xn plus half. That looks true. I like that. Yeah, I think that's good. Yes, and Matt Hancock's jumped in. Give us all some Matt Hancock sort of advice. Great stuff, right, okay. I should stop drawing attention to people's usernames. It only encourages people, right? Okay. Yeah, 2 to the 8 is not 8 squared. Okay, cool. Powers of 2. Is there maybe there's a different way of phrasing that makes more sense to people. Okay, very quickly, I'm going to show you some more rules because I said I would. I think that's what's on my next slide. Who knows? There are a couple more that you learn at A-level. I'm going to chat about them very quickly. There's the product rule. I think people quite like the product rule. It's, I want to say, not as deep as the chain rule. The chain rule I really like. It's about stacking functions together. Product rule says if you've got things multiplied together, then when you work out the derivative, what you're supposed to do is differentiate the first thing, leave the second thing alone, and separately differentiate the second thing, leave the first thing alone, and add those together. When I was in school, they showed me a picture to try and justify this. Let me try and draw you the picture now. So you draw a big rectangle. Haha. I remember what it was like. There we go. There was a rectangle like this. And this was supposed to be, on this side, f of x. And then this is going to be g of x over on this side. So we've got a rectangle, and we're changing the side lengths. Okay. So then over here, this is going to be a little change. This bit of change is going to be something like, it's a little bit like f prime x. And this bit over here, well, it's a little bit like g prime x for the rate of change of these. And then, so this bit over here, let's use colours. This bit over here is supposed to be f prime x, f of x, g prime x. This bit over here is supposed to be g of x, f prime x. And then this bit over here, I actually use purple. It's like I planned this. It's very small. Angry face. Shout out to Olivia Rodrigo, who's got a driver's license. We don't do song references on this show. There's no song references ever on this show. It's not allowed. Right, okay. I think you can make this argument slightly more rigorous if I'm allowed to use some university sort of maths. If anything, this is a good way of remembering this this product rule. I think if you make these roughly equals things, I think if you make these g prime of x, if I'm allowed to say, if this little change is like g prime x change in x, so if you change x a little bit, if you imagine starting at the white rectangle and changing x a little bit, then this distance here will be something like g prime x change in x, delta x, like this. Not sure if I'm going to get away with that. And this thing over here will be a bit more like, I guess you're right, like f prime x change in x. And then overall, you've got loads of delta x's flying around. Request in chat to recolor it using pink. Go on. I don't have pink because. Come on, PowerPoint. Sorry. And then this bit over here will be like delta x squared. So I can kind of make this a little bit more formal. People are like, don't divide by 0. Talking about that. Right, okay, product rule. Good times. There are more exciting product rules. I say more exciting. As exciting as the product rule comes. If you sort of think of it, you can think about versions with like f of x, g of x, h of x, q of x, r of x or something, all multiplied together. Unfortunately, the result turns out to be not that exciting. It's kind of what you might guess once you've seen this product rule for what happens when you put the product of two things. Maybe there's a way to think about this. Maybe this is interesting. Maybe you could think about this as being like a 5-dimensional cuboid thing. You're changing x and it's blowing up every direction of the cuboid shape so that as you change x you get all these different contributions. Actually, there's sort of a nice pattern to the result in the end. My recommendation, if you're interested in trying to work out this, the derivative of this, is to sort of start small. Start with something like f of x g of x times h of x. I might have seen that one in school actually, for the product of three things. In practice, you would think about the product of three things as the product of two things times another thing. There's a sort of recursive product rule thing going on here. Maybe that is cool. Maybe I'm being harsh to the product rule. Okay, and there's another one you learn at school. I've got a couple of minutes, which is the quotient rule. People will talk about a lot. Big debate among people in school about whether you need to learn the quotient rule, which is fx over g of x. It's got this nice derivative. Available in all good formula booklets. You'll find this equation for what the derivative is. There's a kind of debate about whether you should learn this or look it up in the formula booklets, or just use the fact that this is f of x multiplied by g of x to the power of -1, so you know it's like the product rule and the chain rule combined together. So some people refuse to learn this and work it out every time with the product rule and the chain rule. I learnt the rule and now I know the rule, so there we go. Might put one in chat as well. Not chat, in the further reading as well. Right, I'm rambling because I've got extra rules and I've done what turns out I had an unplanned kind of rant about the product rule, but yeah, Leibniz is cross with me now. Sorry, Leibniz. As I think okay, Leibniz, will do your thing. Since you've turned up in chat, we'll do Leibniz's thing, which is Leibniz's thing is if you want to do the nth derivative of this thing. Great to have you with us, Leibniz. Here's the Leibniz rule. Then what you do is you do n derivatives of the first thing, and then you do n-1 derivatives of that thing. But wait, one derivative here. But wait, remember to multiply by the binomial coefficient n choose 1, which we saw last week for some statistics. And this g prime prime x and so on. I've put plus dot dot dot, but there are n+1 terms. It's a very finite sum, like that. Cool. Can I extend the quotient rule to multiple dimensions? I think I can't think of a way to extend it to other kind of interesting setups, right? It kind of doesn't combine with itself in a very exciting way. The product rule has kind of got this thing about you could consider product rule product of different products. That just makes a bigger product, right? The quotient rule, I don't think much interesting happens if you plug it into itself. The chain rule, really exciting when you plug it into itself, using the chain rule multiple times. Right, okay, good. And Charlie wants the derivative of sine x squared, which I assume is some sort of homework, with the chain rule. Sorry if it's not homework. So the chain rule says we want to do the derivative of the outside bit first. So that would be cosine of x squared. What? Times 2x, derivative of the inside bit. So this cosine fact comes about if you measure, if using radians, there's this amazing fact that the derivative of sine is cosine. Cool. Which I don't have time to do now. Right, okay. I think that is the end of today's live stream, or the live bit of today's live stream. I'm going to turn this off. We're going to be back in 167 hours for another one of these, hopefully with a guest. I'm going to try and fix all my technology so we can have guests again. I'm going to hang out in the chat a little bit afterwards to answer admissions questions that I didn't see, or just to talk to people who I didn't talk to live. Big thanks to Flora and Zakai for hanging around in chat. I'll see you in 167 hours. Goodbye.